if the constructal law is correct, then on a larger area, and I'll assume an area that's you have freedom to imagine the shape of the larger area that's fixed. The water flow rate will be, meaning vehicle by the area, will depend on the sizes and numbers of the tree canopies present on it. Not only that, but it will benefit the most from the presence of big trees, right? And so on a equilateral triangle, this is more like isosceles. Hey, do you know what isosceles means? Or where it came from? This is very good to question, okay? Did I spell it correctly or this? Okay, fine. This is good that I spell it correctly. Iso means equal. This is a Greek word. Iso means equal. Isotherm, isoscale, iso never mind. That's equal. Skelos in Greek means leg. So here's a isosceles triangle. But the legs, skelos, is the origin of the word skeleton. Skeleton. So when you go to the doctor and the doctor is looking at your broken, shoulder blade, you say, wait a minute, that's not my skeleton. My skeleton is below my pelvis. Okay. Legs. Equal legs. The equilateral triangle is special. That means equilateral means equal sides. In fact, let me do this even better. Here's a okay. So let's put a big tree. The biggest tree would be one that has 1/3 of it here, another third of it here, and the other third here. And I call, meaning if this were, never mind, the big tree, then you can imagine the rest of the pattern covering the forest floor, and the diameter of the big is called D0. The law says that the tendency is for the ground to put water in the air, and that means that...
So I'm just kind of confused by this drawing.
Louder?
I'm a bit confused by the right-hand drawing, where the trunk is.
Look, I'm modest. Instead of looking at the forest, I'm looking at an element of it, from the assumption that the forest is a patchwork of elements shaped as equilateral triangles. Okay. And on one of those elements, of a length scale capital X sub t, meaning triangle, I'm now planting or imagining the presence of trees of multiple scales. The D0 tree is here, and I have how many of the D0 canopies? 1/2. 1/2, because 1/3 plus 1, no, this is 60 degrees out of 360, so this is 1/6. So I have 1/2 D0. And the D0 is key because the length scale is proportional to the mass flow rate that goes upward. And then there is this empty space that's inviting smaller vegetation to grow. The next size down is called D1. And there will be one D1. You notice here, from the biggest to the next, the number of the next smaller is greater. And then there are smaller and smaller and more numerous armpits, such as here. And I'll call these even smaller ones D2. How many D2s do I have? I have 3. This is this is how the aha becomes louder and louder. You start with a fixed element of area, and on it, from the constructal idea that what happens naturally is toward more and more of this. Well, obviously, if armpits proliferate, and they proliferate in the direction of more numerous and smaller, then this summation continues toward obviously smaller and more numerous. In the book, this drawing is called Figure 1032A. And okay. And then comes, as I said already, it's one of the good things you can do to yourself in life is to question yourself, so you don't end up one of these ideologues who know only one thing, and then with that idea they march over the cliff, and say, gee, wait a second, I was too cheap. Another way of trying this is to say, well, maybe these trees are arranged in a square pattern. So the area element is a square of side x sub s for square. Okay? And again, instead of this kind of beginning with D0, this is easier to draw. And we draw that, and then that, and that. This way, the D0 altogether will be, meaning pumping water upward, meaning toward you, will be one of these D0 contributions to the mass flow rate. And then the armpits, plus the next size is D1. 1, D1. And then the story gets interesting because the even smaller size, called D2, will impress us with a factor of 4 in front. So that's D2. Showing again that what happens is that the sizes of these contributors become smaller, or as they become smaller, their similar or identical brothers become more numerous. You see that the armpits proliferate steeply.
Can you just take the limit of the series and just assume it's the whole area that gets used?
You mean to infinity?
Yeah, kind of.
Yeah, I told you about infinity. Remember that demonstration from going back to the old Greeks? Infinity means is jargon for I do not know.
Oh, that's right.
Yeah. Which is why wise people cut it off. They say, well, let's assume that the number of terms is large, but yeah.
Where do you draw D3 on that?
What now?
Where do you draw D3 on that?
Would you speak without talking, without chewing?
Where do you draw D3 on that? Where are you going to draw D3 on that?
Like the next set of circles.
The D3?
Yeah.
What's the armpit for D3?
Oh, here they are. 1, 2, 3.
No, but the two armpits on the inside is smaller than the armpit on the outside, right?
Yeah.
There's 1 D1, there are 4 D2s, and then D3s would be these. And there will be 3 times 4, meaning
No, do you
12.
think the armpits on the inside is the same size as the armpit on the outside?
I don't follow, yeah.
As in, like, is the size of that and that the same size as that? Because it doesn't look like it.
Well, the D1 is supposed to be tangent to all the other Ds. There are points of tangency that when there are 3 coming together.
But the radius of this one is not this one.
It's not, no. D1 is different.
Yeah. So that means this area doesn't necessarily equal to this area. Do you think?
Okay, I think you're right. Yeah.
I don't know.
Yeah, right. You're right. But there we go. Well, so once again, diversity galore, meaning it's worse than I thought. Whatever. This is definitely bigger than a bigger number, the so-called D3 plus. Anyway, the point is that this combination of smaller, as they get smaller in this sequence, they get more numerous. And this tendency toward not only diversity, that's pretty obvious, but hierarchy, because the big ones are few and the smaller are many, emerges in the mind, in this case visually, from invoking this idea that the arrangement of producers of water on the area is free to change. In the book, I showed that you can play with this square all you want, and not start with a size that's the biggest that it could be if centered in a corner. You can start with a size that's big but not the biggest. For example, this size, this is D0, and then another D0 here, and D0, and then D0. I made this move recognizing from the first 2 examples that it helps if you have more of the large size trees with which the sequence begins. And if you start this way, then you'll have another big tree in the middle, which this time is called D1. Get it? And then another armpits that are big for another scale called D2, much bigger than the previous. So this will be D2. And then, of course, a huge population of smaller. These would be D3. So, and then you can write another sum. So that's the first writing based on triangular elements. This is the second based on square. There is a third. I'm not spending time on that. And then I'm not looking at, I'm not a forest scientist, I just have pencil and paper. And then I made this drawing, which is a log representation of what I have been spelling out in words. On the on the ordinate, I indicated the size of this, the length scale of the projected canopy. The length scale, the biggest, you can see here is the D0. And I call that biggest size 1, and then going down in cycles of 10. And on the ordinate, so this is log. On the ordinate, I indicate the rank of each size. The biggest in this case is the first. So number 1 here means the biggest. And then the one ranked the 10th, meaning one of the ones from here, would be here. And then the 100th. And if you go almost blindly, not blindly, you have to read these expressions, you discover that that each population from these 3 examples falls in a balloon, like that. They fall this way, because every drawing is based on assuming a population of a certain size called the D2, for example. Anyway, these horizontal bars fill an area that say graphically what I wrote here, that the smaller are more numerous, or that the answer to the tendency is few large and many small. And this is the one way to say that hierarchy is a natural phenomenon. So hierarchy, natural. On this blackboard, it is predicted. It is discovered. So predicted. Not copied from like reading maps or maps of the forest floor. There is at least one such map that was published a long time ago. It was about the distribution of sizes versus rank of all the cities over Europe. What do the cities over Europe do to the atmosphere? They put the water back and other things back into the wind, and it's the same drawing. But to look at the map and the actual map, and then make this sort of representation is to do empiricism or description. In my own life, it came the way that I put it on a blackboard, from invoking an idea and then testing it. And out of it came this prediction. The important thing to retain is what I wrote here. The hierarchy is a natural phenomenon. It is one of many phenomena that support this principle of architecture, occurrence, and then evolution. If it has freedom to change and go with the times. All of this, an invitation for you to read the book Freedom and Evolution. Which is kind of a funny book. It's the thinnest of the books I wrote. It's the thinnest because Springer decided to use a very small print. But I think it's my best book so far. All right, so that's the goodbye to the sequence of predictions from the root shape to the trunk and canopy. In this case, the design of the forest floor. If you question these things, you come up with answers to dilemmas with which people struggle every day. For example, in agriculture, people plant crops according to designs optimized from departments of I don't know what, agriculture and universities. Orchards, when planted, are beautifully landscaped. And every year, because you cannot manicure them every week, every year the orchard has developed babies. Shrubs, weeds grow in the spaces at the intersection of the canopies of those valuable plants. They always appear. And they do because the piece of ground that was neglected has the tendency to configure itself to offer its water upward more effectively.